All right, so in this video, we're going to introduce the idea of NMR, or nuclear magnetic resonance. Out of all the different spectroscopy techniques, NMR is probably the most powerful tool for figuring out organic structure determination. When we were, for example, thinking about IR did a really good job at giving us an information about what functional groups are present, but they don't give us any idea about where that functional group is on the molecule. You don't know anything about the connectivity, how that molecule is actually connected, what's next to each atom. NMR actually gets us a lot more information. It can actually help us determine how things are actually connected. Now, NMR is looking at a specific nucleus. That's where that nuclear word comes from, not nuclear as like radioactive nuclear, but nuclear as looking at a nuclei. And it is looking at how nuclei respond in a really strong magnetic field. You can look at a bunch of different nuclei. We are going to primarily focus on proton NMR, which is just a hydrogen. You can, though, use a variety of different nuclei. Carbon 13, nitrogen 15, fluorine 19, phosphorus 31, and so much more on the periodic table, which is one of the reasons also why this is such a powerful technique. One thing you'll note is if we look at all of these different nuclei, they all have a specific odd number. And that odd number is actually really, really important. You can only look at your odd number isotopes. So, for example, carbon 12 is much more abundant than carbon 13. Carbon 12, though, is not NMR active. We actually need to look at that carbon 13 nuclei because of its odd number. And that odd number is something that is super important. Proton is nice and easy. 1, that's an odd number, so nothing we need to do extra there. So when we kind of think, and this is just going to be a really quick, kind of super high level kind of discussion on why we get signal. For IR, I think it's a lot more intuitive, where you hit something with energy and it kind of jiggles a little bit. NMR is a little bit more abstract. So here we have an example of a bunch of different nuclei that have a spin direction. Back when you were thinking in general chemistry and we're thinking of quantum numbers, you could have a spin 1/2 plus or minus, and that's an up spin or a down spin. We're kind of getting towards that here. You can have in your normal structure, if you just have a little vial that has a bunch of molecules that have a bunch of protons, they can be spinning in any random direction. Now, if we take this and we put this in an external field, so we have a really, really strong magnet, those spins are then going to align. And here we have what is known as an alpha and a beta spin. Think of this as a spin up and a spin down. And there's an energy difference between those. And what we can do is we can actually look at those differences in spin upon that alignment and get a bunch of really, really important information. Now, in order for this to happen, we do need that really strong magnetic field. And to do this in the actual spectrometer, and in class I'll actually show a few pictures, including the one that we have here on campus, you need a very, very strong magnet. So this is a very large device. The one that we have is a 300 megahertz, or we have 400 megahertz, sorry. 500s, 600s are somewhat common. These are expensive. We're often looking at hundreds of thousands of dollars. As you get higher and higher in terms of your megahertz, you're able to actually pick up and differentiate things much better. As you can see here, an 800 megahertz or 900 megahertz are in the millions of dollars. Now, because of the fact that this is such a strong magnet, we do need to be super careful. So, like, if you have a pacemaker, you'll see actually on the sign to the lab, like, hey, if you have a pacemaker or any like metal implants or stuff like that, like, don't go in this room because we have a really, really, really strong magnetic field, which we need in order to see the unique signals associated with all the different protons in different environments. So one of the kind of unique things and why this is really powerful is, unlike NMR, all your alcohols are all going to vibrate kind of like the exact same and kind of be in the same area. All of your protons, or whatever specific nuclei you're going to look at, are actually going to come in a bunch of different ranges depending on their environment. your external magnetic field will be set. So for example, 400 megahertz. However, the things that are around your molecule, which is what our neighbors are, things that are connected to your molecule, are going to impact that magnetic field and then provide shielding. And that shielding is going to change how your molecule interacts with that magnetic field based on the environment. And each of the different protons are going to be in a slightly different environment and feel that magnetic field differently. And that's actually how we can differentiate our different signals, depending on how strong or weak it feels in the magnetic field. I want to show the spectra first. So here is kind of an example of a typical like NMR. On our x-axis, we are going to be plotting something known as chemical shift. I'll define that in a minute. And that's has a unit of part per million. That's relative to your the frequency difference between the effective and the actual. And this is plotted much like IR in a backwards realm. So 0 is going to be far to the right, and the numbers are going to get higher as you go to the left. Typical range for proton NMR is going to be between like 0 and 14. When we move to other nuclei like carbons, you can get values in the hundreds. If you switch over to fluorine, you often get numbers in the negatives. It can vary often a bunch depending on what nuclei you're looking at, but we'll generally be the 14 to 0 range, 14 being on the far left and 0 being on the far right. Things that are on the left are known as downfield. And then things that are on the right are known as upfield, kind of like uptown and downtown. So downfield has really high numbers, but it's kind of like to the left of the plot, and then upfield has low numbers, but it's to the right. And then our y-axis is going to be signal intensity. So we actually won't even show that most of the time. It's just a number of counts, and it's pseudo-relative. Things like the integration, which we'll talk about, are going to be a lot more important than the intensity. So unlike your IR, our baseline is going to kind of be at the bottom, and then we'll have a spike that will appear or come up if your molecule if you have protons in that environment. So if we kind of consider, for example, of the different peaks here, this is an example of methanol, so CH3 and then an OH. Here there's a total of 4 different hydrogens, but there's only 2 unique environments. One is shown in pink here, a hydrogen connected to an oxygen. It has signal associated at a specific spot here, 3.2 part per million. And then all 3 hydrogens that are connected to carbon are in the same environment, so those will all peak around this 1.2 part per million. Now, the reason that they'll actually be at different ranges is because of that differences in shielding. And I have here the same molecule shown, just kind of, I guess, flipped. And when we think about the idea of shielding, we see that oxygen is our electronegative atom. It's pulling electron density towards it. And what that's going to mean is it's going to make the things around it more exposed. It's going to be deshielded. So if you're close to things that are electronegative, you're known as deshielded because your electron density is being pulled away from you. So you're more prone to feel that impact of that magnetic field. Where if you're farther away, then you're more shielded or you're blocked from things. So the H that's connected to that's part of the alcohol is more exposed, and you'll see that is why with this pink proton that it is at a lower field or more downfield. That also is a higher number, depending on how it feels the increase of that magnetic field. So in terms of what we can pull out from the spectra, there's a handful of really, really important things that really help us figure out our details about our molecule. First off, the number of signals is super helpful. Every time we get a signal or a peak, or collection of peaks, and sometimes when we talk about splitting, that is going to be associated with a unique population of protons. And one thing that we're going to focus a lot on in class is identifying those different populations with things like HA, HB, HC, as these different groups of protons that share the same environment. Next, where they're located gives us a ton of information. That's telling us if it's shielded or deshielded. Things to the right are having lower numbers, which are going to be things that are more upfield are going to be a lot more shielded. Things that are to the left or downfield, higher numbers, are going to be a lot more deshielded. The intensity can give us some information, but the integration is actually even more powerful. Integration is going to be the area underneath the curve, and the relative ratio of those integrations will actually tell us how many protons there are in each signal. And then, not this class, but next class, we're going to talk about multiplicity or the splitting. A lot of your peaks are going to have a unique pattern. That's not just going to be that nice single peak, and that's going to give you a bunch of information about the neighbors or the amount of those nuclei, in this case protons, which are one away from the specific proton of the signal you're looking at. Now, that chemical shift, which is our x value in terms of our plot, that is going to be the value which is showing the impact from your magnetic field. It's going to be a part per million, so it's just a ratio, and it's the shift between your standard and then the total spectrometer. So this can actually change based on your spectrometer. So your denominator will be kind of a set number, and then your numerator will be kind of a value based on a standard. The main standard we use is tetramethylsilane. So that is a silicon that is surrounded by 3 methyl groups. In this case, this is considered a really shielded molecule. There isn't anything super electronegative. They all have pretty similar electronegativity. So this is a molecule that we will always give 0 part per million in terms of your peak, and you'll often see, like in here, you see that little peak at 0. That's associated with a standard of TMS. Often your solvent, which in most cases for us will be deuterated chloroform, it will be spiked with a super small amount of tetramethylsilane to make sure that we set it directly to 0. One other nice thing about this is you'll see that there are 12 equivalent protons. All of those H's that are part of the methyl are all going to be in the same environment. So you can add a really, really small amount, something like 0.03% by mass, and still actually get a big enough signal so you can actually see. And that's going to kind of be our reference point. Now, when we're thinking about chemical shifts, and we'll maybe focus on this right graphic first. As you start to add electronegative stuff, you can see how you can change the environment. So here we have 4 different examples. We'll call this molecule 1, molecule 2, molecule 3, and molecule 4. And each of these is going to be a carbon that has some number of hydrogens. In this case, all these hydrogens are equivalent. And if you look at just simple methane, it's going to have a chemical shift that is sitting right here at 0.2. So it's going to be very similar. It's going to be super shielded. It has nothing electronegative, nothing unique. So it's going to be pretty similar to where that tetramethylsilane is. Now, if we go in and we start to add something that's electronegative, here we're going to add that chlorine. That chlorine is going to have 3 sets of lone pairs. It's going to be pulling electron density towards it. So this is going to now have a dipole. Those H's are now going to be more exposed because that electron density is being pulled away from them. And we'll see that it shifts to a higher value or more downfield, in this case having a chemical shift of 3. We can continue this process, and for example, if we look at a molecule that has 2 chlorines, we shift it even further because those H's are now even more exposed. In this case, we have a chemical shift out in the range of 5. And then we can go even further and have a 3. This is the structure of chloroform, which is having a absorbance, or not absorbance, a chemical shift way out at 7.2. So while this gives us a lot of information thinking about how close or how many electronegative stuff there is, this does add a little bit of complexity because when we think back to like IR, if there's a peak around 1600, we know it's a carbon-carbon double bond. Here, we're just thinking about a proton being connected to a carbon. It can have a wide range of shifts depending on what its neighbors are. So there's not kind of like the same hard and fast, like, oh, this section means this specific type. There is an attempt to summarize some common themes over on the right side here of where some common stretches are. But I don't want to spend too much time on that, and please don't memorize these. We'll focus a lot more on trends, and we'll show that a lot with the problem solving. I'm going to show another example here. Here's the structure of butane and 1-bromobutane. The only difference is this H here was replaced by this bromine. In the case of our simple butane, the two outside CH3s, which are the methyl, I'll go ahead and maybe show this in a different color. These blue ones, which are the outside, and then these green ones, which are the inside. The outside protons are the most shielded, so they'll have 0.9, and then the inside will have 1.3 for their chemical shift. Now, if we simply change that H over to a bromine, we'll see that these are actually now all unique, and all of these are now going to have different types of stretches in different locations. So the alpha position, which is 1 away from the bromine, those shift all the way up to 3.4 because they're really deshielded because of the electronegativity of the bromine pulling electron density. The beta position, which are shown in green here, get a small shift over to 1.7. They used to be 1.3, so they're now a little bit more deshielded. The impact is less because of the fact that it's further away. And then once you get over to like the pink, which are your gamma protons, you'll see that there is no real impact from that bromine because of how far away it is. So this can give you a lot of information about like proximity. The one last thing we'll talk about in this video is a little bit about how you can be deshielded without an electronegative atom. Normally we think about something like a bromine or a chlorine or an oxygen or a nitrogen, but the movement of electrons through resonance also can impact a lot. So your vinyl bonds, which are going to be protons that are on a double bond directly. So if you have a double bond, thinking about the hydrogens that are directly connected, those are known as vinyl. Those are often in like the 5 to 6 range for ppm. And then your aromatic, especially like your benzene protons, those are going to be shifted all the way out to like the 7 to 8 range. Here, you don't have a electronegative atom, which is pulling electron density, but you do have movement of your electron density because of the fact that you can do things like resonance, and you can have that impact on that magnetic field that leaves those protons extremely exposed. So things that are on double bonds like vinyl or on benzenes do actually have some pretty unique locations. The one last thing about locations are hydrogen bonding. So for hydrogen bonders, your OH and your NH, the temperature and the concentration will actually have a huge impact of where they are. You can have a hydrogen bond actually change its chemical shift based on either the temperature or the concentration. As you increase the concentration or decrease the concentration, you change how much hydrogen bond is able to happen. So that's why they're in different environments. And one way to actually figure out if you have hydrogen bonding in your sample is to actually take the same sample and then measure it at a bunch of different temperatures. And if you see peak shift as you change the temperature, that can be a big hint that there is a difference, that there's hydrogen bonding present. So the hope right here of this video is just to give you a little bit about background. We are going to focus a lot on these kind of 4 major themes when we're trying to figure out our molecules, how many signals there are. And we're going to focus a lot on that in class when we're talking about the number of equivalent protons. The location of the signals, which we kind of just talked about with our chemical shifts, and we'll get a lot of practice when we're actually solving. The size of those peaks, especially the integration, we'll talk about that when we're solving. And then our signal splitting, our multiplicity, which we'll talk about in our next video. So I think that's a good spot to kind of end after some introductions, and then we'll pick back up in the next one.